Hey guys, so this is video 2 of chapter 4. I'm picking up on slide 8 of the PowerPoint. So we just talked about sodium chloride dissolving in water. When it breaks up, I get sodium ions floating around, I get chloride ions floating around the solution. So now we'll move to another compound. If I dissolve potassium sulfate, which potassium ions have a +1 charge, sulfate has a -2 charge. So the formula of that compound, which you should be able to come up with, it'll be K2SO4 to neutralize the charges, which means if I have a crystal of potassium sulfate, it's going to have, for every one sulfate ion, it's going to have 2 potassium ions in there to neutralize it. It has to be a 2-to-1 ratio. Okay? Now, if I dissolve potassium sulfate, at the bottom, you can see the reaction here, where if I have solid potassium sulfate initially, I add water. Now this is more of a physical change than a chemical reaction here, because I'm just changing the physical state of solid potassium sulfate. I'm making it aqueous potassium sulfate. Okay? But when it dissolves, there is a significant change that occurs where I add the water. Now, again, the water is not going to show up as a reactant or a product. It's just helping me change my physical state. That's why it's on top of the arrow in this reaction, because it's not a reactant or a product. This isn't a true chemical reaction here, okay? But I add the water, potassium sulfate changes states, but also the ions come apart. Now, what we might notice here, number one, the potassium breaks off, but the sulfate stays a group. SO4, when it dissolves, that sulfate ion does get dissolved into the solution, but those atoms stay together. Okay? That's kind of why we learned the polyatomic ions in the first place, is that as we move through these physical changes, when we do chemical reactions, if sulfate exists on the reactant side, it's pretty common that even after we do a bunch of chemistry, we're still going to have sulfate on the other side, because those atoms are really stable together. They like to stay together as much as they can. So it's kind of like in high school, there's a group of people that you never see one of them without the other ones all around. They're kind of like a little clique, or kind of a gang that they're always together. We're going to say a gang in a good way. When it dissolves, the potassiums separate, but the sulfate stays together. Okay? They all float around the solution. So what I see in my beaker up here, once I dissolve my potassium sulfate, I have, and again, this is if I dissolve 2 units of K2SO4, I have a sulfate ion and a sulfate ion. And if I have 2 sulfates, remember in my original compound there were 2 potassiums for every sulfate. So if I have 2 sulfates in there, I should have twice as many potassium ions. 1, 2, 3, 4. That is my 2-to-1 ratio. So no matter how much I dissolve, there should always be twice as much potassium as there is sulfate. If I dissolve 1,000,000 units of K2SO4, I'll have 1,000,000 sulfates floating around. I'll have 2,000,000 potassium ions floating around in that solution. Okay, so we're going to maintain that ratio no matter what we do. Now, when we move on and do reactions, okay, so this is going to be a double displacement reaction where I'm mixing together. I have a beaker of silver nitrate and I have a beaker of lithium chloride, and when I pour them together into a bigger beaker, a double displacement reaction occurs. Okay, now how does that happen? Well, we kind of have to think about how these things really exist in solution. Okay, so I have my first beaker. I just said it's silver nitrate. So in that solution, if I dissolve silver nitrate, which is an ionic compound, then I should know the ions, once they dissolve, they're not really together anymore. It splits apart as it dissolves. I'll have silver ions floating around and nitrate ions floating around. So in that beaker, I really have Ag plus and NO3 minus. I have a bunch of those floating around in the beaker. And in my other beaker, that was the one that said lithium chloride. So that one, again, is a soluble ionic compound. We've dissolved it into solution. So I need to know that that's Li plus ions and Cl minus ions floating around. So when I pour them together into a bigger container, okay, so now all that solution, this solution, they're both together. So now I have Ag plus NO3 minus Li plus and Cl minus all floating around that solution. Well, very quickly, the silver ions and the chloride ions, as they're moving around and kind of bumping into each other, because remember, in a solution, all the particles are moving all the time. So whenever a silver and a chloride ion come together, we know by the solubility rules that silver chloride is not soluble. What that means is the attraction between silver and chloride is so strong that even though there's water molecules all surrounding them, the silver and chloride are going to come together anyway. They can't help it. And then they're going to, once they come together, that's a neutral compound that's going to drop out of the solution. So very quickly, this is going to change. Instead of having all the ions floating around, what I'm going to have instead is I'm going to have some solid on the bottom. That'll be my AgCl. But then my lithium and my nitrate will still be floating around separately. Okay? So, now, initially when this happens, when I mix them together, if you watch the videos from lab that I posted under experiment number 5, I think, if you watch those videos, you see that when I mix two solutions together, it forms a precipitate. The whole solution turns cloudy because these ions are going to come in contact with each other everywhere in the solution. The solid particles are going to form all throughout the solution, which is why the whole solution turns cloudy and you can't see through it anymore. But if you wait a little while, all those heavy solid particles will settle to the bottom and it'll end up looking like this. The solids on the bottom, that's my silver chloride, and then I have lithium ions and nitrate ions floating around. Okay? Now, that process, we need to go back to the PowerPoint and look at reactions to see how are we going to get our reaction to represent all this stuff that's going on. Because if we just do a double displacement reaction, we just say AgNO3 mixed with LiCl, we swap partners and we get the two products, but we're glossing over a lot of stuff that's important that's going on. So we have a process that we're going to show that. All right, so our balanced equation, you should be able to come up with this on your own, that if I tell you what the reactants are, you should recognize that's AB plus CD, the pattern, know that you need to switch partners. The cation from here and the anion from here are going to go together. The cation from here and the anion from there are going to go together. There are my products. Make sure you check your charges. Keep the polyatomic ions together. You know, all that stuff that we've talked about before. So, and then that is a balanced equation. So if I mix together silver nitrate, lithium chloride, I form my two products, then I should know my solubility rules to say, oh, silver chloride, I know chlorides are usually soluble, but not with silver, mercury, or lead. So that one's going to be a precipitate. And then with lithium nitrate, I know that lithium is a group 1 metal. Group 1 metals are always soluble. So that one's aqueous. Okay, so that gives me my reaction. That's the normal balanced equation. So if I say write the chemical reaction, that's it. But in order to get a better view of what's going on, we also want to be able to write what's called the total ionic equation. Okay, now the total ionic equation, I'm going to basically break down each of these things to be a more realistic representation of the pictures I drew on my board. So I'm going to start out and say the silver nitrate. So the silver nitrate in the first beaker, in reality, if I say silver nitrate AgNO3 aqueous, it makes it look like that in that solution there's one compound. That's not really true. In that beaker, there are actually two ions floating around separately. Actually, two types of ions. There's a lot of ions in there. Half of them are silver ions and half of them are nitrate ions floating around in solution. Okay? So I really, in this beaker, instead of writing AgNO3, which makes it seem like they're together, I would rather split them apart and say, okay, the first beaker contains Ag plus ions and NO3 minus ions. Okay? And then the second beaker does not contain the compound lithium chloride. It actually contains lithium ions and chloride ions separately. Okay? So that's, if I look at the reactant side of the total ionic equation, Ag plus aqueous plus NO3 minus aqueous, those are the two ions that were in the first solution. I mixed it with the lithium chloride, which is actually Li plus aqueous and Cl minus aqueous. Okay, so once I mix it, all four ions are floating around in the solution. And at that point, once they're all mixed together, that's where I can look and say, oh, but you know what? The silver chloride, when it comes together, that's the precipitate that forms. That's why the solution turns cloudy, and then it settles to the bottom. But then, where normally I thought in the original reaction, it looked like I was forming a second compound. But really, if I form an aqueous ionic compound, that's not real. If you look back at my picture, when I finished, the lithium and the nitrate never really came together. They're floating around separately, so that's a false product. It's not forming in the solution. The silver chloride is forming, but the lithium and the nitrate, they're still swimming around doing their own thing. They don't even notice each other in there. So to put them together like that is misleading. The total ionic equation is a much more accurate representation of what's going on in the solution when I mix these together. Okay? Now, the last step is where I would say, okay, well, the total ionic equation shows me the whole story, but what if I only want to see the important part? What's the important part of this story? Well, really, the first solution had silver ions in it. The second solution had chloride ions in it. And when I mixed them together, the silver and the chloride came together to form the solid. So I'm going to mark out the things that basically didn't do anything in the reaction. In the first solution, nitrate was just swimming around doing its own thing. When I finished, nitrate was still just swimming around doing its own thing. So nitrate didn't really do anything. He was there in the beginning, he's still there in the end, just swimming around. So we call that a spectator. He was present for the reaction, but he didn't do anything, he just watched. So he's called a spectator ion. All right? Lithium is also a spectator ion. He was freely floating around in the beginning, he was still freely floating around at the end. So we're going to get rid of those because they didn't really do anything, and that's going to boil it down to what we call the net ionic equation. So the total ionic equation shows everything. The net ionic equation, I'm going to cancel out the spectators, which I only cancel out the things that appear exactly the same on both sides. Okay? Now the key here is, if you're not careful about how you label everything in the total ionic equation, putting the physical states and the charges, balancing the equation properly, if you don't do all that right, then when you try to cancel things out, you might get confused and cancel the wrong things out, and it's going to mess up your net ionic equation. So what I notice is if I get rid of the nitrate and I get rid of the lithium, this is like the summary, like the cliff notes of what happened in this reaction. Instead of writing out the whole novel, if you just want to know what was the real quick summary, basically I mixed together a silver solution with a chloride solution, and it made silver chloride. The other ions that were there weren't really that important. So if you tell the summary, they get left out. Okay, so that is going to be a test question for you guys coming up, that you're going to have a reaction, that you have to write the reaction, write the total ionic equation, and then write the net ionic equation. Okay, I'm going to cut off the video, but the next video we'll have 2 more problems to practice this, just to see different variations of it.